Why don't you do it?
Yeah, sure. Yeah. So we're very thank you all for coming to this Discrete Math seminar. We're very happy today to have our UMass undergrads talking about their summer work in Discrete Math. So we start with Peter Cassels, who was advised by Guy and myself. So we're going to talk about multivariate hook formulas for Skew and Tableaux. Go ahead, Peter.
Great. So I'm Peter. I'm talking about hook formulas for Skew Tableaux. Like Alejandro said, this is work I did this summer. So thank you to him and Guy for advising me. So I first just wanted to lay some groundwork, conventions, notations, and that sort of thing. So when I say partition, all of our partitions are going to be non-increasing. And then, so associated to the partitions, we'll have Farrow diagrams or synonymously Young diagrams, which will just be the partition sort of laid out in a graphical sort of way with empty boxes. So just sort of visually, when I say partitions, I probably mean these shapes of empty boxes like this. And then reverse plane partitions, RPP. So these are when we fill in those empty boxes with non-negative integers where the rows and columns are both weakly increasing. And then the size, those absolute value bars are just the sum of all the entries. I guess I have to be a little careful when I use those bars because sometimes it means the size as in the sum of the entries or the number of boxes, but I think it should be clear based on the context. So for example, I wrote out all the RPPs with shape 2, 2, size 3. Of course, this is a finite set when you restrict it that way. Semi-standard Young Tableaux, SSYT. So these are a special type of reverse plane partitions where the columns are now strictly increasing, but the rows are still weakly increasing. So from the ones on the last slide, only one of them was an SSYT. Then standard Young Tableaux, a special type of SSYT, where we fill in the entries bijectively. Sort of one profitable way to look at these diagrams is the hooks and the hook lengths. So the hooks just...
sorry, Peter, in the previous one, so you put them bijectively, but are there any restrictions on how you put them?
Oh, of course, yes. So there's still SSYT. So we still have, well, now necessarily strongly increasing rows and columns. So these are just two examples, one way we could do it. So sort of the hooks are just this set of entries. Are people able to see my cursor?
Mm-hmm.
Yes. So the set of entries below or to the right of, including the entry. So we associate the hook to an entry. Said that. So in this example, at the cell 1, 2 or entry, we have these 4 cells are part of the hook. So the hook length is 4. So there's a famous way to enumerate the number of standard Young Tableaux, first given by Frame, Robinson, and Thrall. And then there's an array of other proofs, some simpler than others, including probabilistic proof, bijective proofs, algebraic proofs, that gives the number of standard Young Tableaux of shape lambda, which is sort of as simple as you could hope, just n factorial times product over the cells, 1 over the hook length. Richard Stanley was able to find a Q analog of this, summing over the RPPs, and then Q over Q to the power of the size of the RPPs is just the product 1 over Q to the hook length. Again, you have to remember that here the size is the sum of the entries.
So what happens when Q is 1 or in the limit? How is it a Q analog? Exactly.
Oh, so when Q is 1, it gives you sort of the formula on the previous slide. And then I don't know if there's as much of an interpretation for sort of arbitrary values of Q. Of course, we might have some divergence issues, but so did that answer your question?
Yeah, I was just the right-hand side. I was just trying to understand how that
yeah, so I guess
related
it
to the previous
sort of have to
one.
do with like the famous way to enumerate partitions, 1 over 1 minus Q to the n in that case. Sort of that have like the geometric series. So after Stanley's proof was proof given by Hillman and Gressel, which proved this bijectively, giving a bijection between these arrays A lambda, so natural number arrays, here 0 is a natural number, such that the size, we have the sort of relationship between the size of the partition and the hook length. So here's sort of the way that the bijection works. I put an example in 2. Sort of we have these arrays pi I and, or I should say RPP, pi I and arrays AI, and then we're counting. So we create a path, and then what we do is we decrement all the entries of pi that are in our path and increment the ones in A on our path. Sort of with these rules. So I guess we can start with this example that start at the southwestmost non-zero entry of pi. Oh, of course, we're starting pi 0 is the initial RPP, and then it will eventually end up with phi of pi. So the Hillman-Gressel algorithm applied to pi. So for this example, we're starting at the southwest entry, southwest non-zero entry. Then we move upwards, north, if the entries equal, and else we move west. And then we terminate our path when we can't move west or north or west anymore. So for example, at this first one, well, we can't move north because they're not equal, and then we have nowhere to move west. So our path is just the single entry. So we decrement it over here. And now we can move north, and then we move all the way west. Oh,
so
east,
is
sorry.
east
Yes.
west for you, Peter, or?
Yes, sorry. I just noticed that. I think my issue was there's not really consensus in the literature which way is the Hillman-Gressel algorithm and which way is the inverse. So I think when I was copying down the instructions, I was looking in the wrong direction and then changed some things, but evidently not enough things.
That's okay.
So yes. So I guess in reverse orientation, it should be east. Yes, so then we make this path, do the same thing over here, and then thank you for the correction. And then we finally end up with this final array, which does in fact satisfy the relationship that we were hoping. Hopefully that adds up to 12, the entries times the hook length. So now we're also going to be talking about skew partitions. So these are the ones where we sort of block out anything of a smaller partition. Yeah, and then when I say like a partition is contained in the other partition, that just means that we can sort of fit it in that way.
So sorry, Peter, could you repeat again why the weight is the same? So the property of the, so how do you weight, how do you compute the right-hand side?
So the right-hand side would be, if this equation is just the sum of all the entries, the sum over U times their hook length, which it's sort of like we preserve it in each step. So, well, it's sort of like the number of times that we're incrementing something is, or decrementing things in pi will be the size of pi, because everything is incremented once, which is really what that equality is saying. And then it's sort of like we do that many times when we're creating A, except we have to double count all the hook lengths. So that's why we have a weight of h of u. So now skew partitions, sort of just partitions where we sort of disregard a smaller partition inside of it. And then to these skew partitions, we have excited diagrams where sort of the main idea is just you start with the initial skew diagram, and well, you start with the mu, so the blue part is the excited diagrams here. And then whenever we have a situation where we have a cell in the excited diagram where the cells to the right below and right below diagonally is not in the excited diagram, then we just move it there, and then we just fill in the rest of them recursively. So here we move this cell down here. And then we do that again for this cell, because now this cell. Then Nerissa gave a formula for the number of standard Young Tableaux of skew shape for a given size is this one. So the size of the skew shape, and then sum over excited diagrams. It's the product one over hook length. Sort of, and then again, if you take mu as the empty set, or even mu to be the partition with just a single box, then we get that this gives us the frame Robinson enthrall sort of normal formula. And then Morales, Pack, and Panova introduced the broken diagonals associated to the excited diagrams, just given by, so here the broken diagonals are the cells with the lines through them. So for this broken diagonal, we start with the normal ones and we move it over. So I think sort of the metaphor people use is sort of pushing the diagonals in, move this one all the way over, and then fill in the diagonals again, do that again. And then eventually we sort of run out of skew partition or excited diagram, these ones at the bottom. They gave bijection, sophisticated algebraic proof of this result, that the Hillman-Gressel restricted to the SSYT gives us a bijection to union. So the arrays with support in the broken diagonals of so sort of the, yeah, so the image is exactly the any array with support that has in the broken diagonals. Oh, sorry, I said that incorrectly. So support contained in I want to make sure I'm saying this correctly. So it's all the arrays that have non-zero entries in the broken diagonal, and then all of the possibilities. So what I was doing this summer was working towards proving this purely combinatorially. So sort of taking inspiration from their paper, the way I did this was making a definition of all the diagrams which have support from Hillman-Gressel of the SSYTs, calling them Q of lambda mu. And sort of what we were able to prove, except for one sort of technical lemma at the end, was that these are given by this formula. So again, the entries with, or the arrays with non-zero entries in the broken diagonal, and sort of all the possibilities given the power set. Then sort of changing gears a little bit to sort of some generalizations of this particular multivariate analogs. Gansner, 1981, gave this multivariate analog of the formula for the Q analog for RPPs. Now I guess it's a Z analog. We have that multivariate Z. I know this is sort of like a mess of notation, but again, if we have only one variable, it gives us the Q analog, which in turn gives us the frame Robinson enthrall. And then and then the multivariate analog of the SSYT case given by this formula, I guess more or less just counting out all the entries with the broken diagonals and then taking the total number of them.
So Peter, do you have an example of some of these things with multivariates, or?
I actually didn't work out any examples, but I guess I can.
Okay, just wondering.
Yeah.
And so the proof of that, Peter, is combinatorial, or like you're enumerating things on both sides, or?
Yeah, so the proof of this one is combinatorial given Alejandro's result. So I guess sort of transitively not completely combinatorial, but filling in sort of the ends. Although the work I did was purely combinatorial. So does anyone have any questions or?
Yeah, could you go back to the multivariate? I think that was on the previous slide. I didn't quite catch the definition. So you're taking Z. So the index is what's C of V?
Oh, so this is the C is the content. So the just sort of like indexing the diagonals. Yeah. So everything like along the main diagonal would be content 0, and then.
Right. Okay.
So
So we're sort of like indexing the variables by content is sort of like the multivariate way of thinking about it. Instead of taking like every cell to contribute equally, the cells contribute as they're indexed by their content.
So
how have you defined, is that, what's the notation? On the second notation equation, you have z to the power, what do you call it? Sigma of v.
Oh, okay. So I did, I guess, switch from pi to sigma, but those sort of are both in RPPs or SSYT, depending on the context.
Define sigma of v. I kind of lost it.
So sigma of v. Oh, that's just the so if sigma is a RPP, then that would, and then v is a cell, so it's just the entry in that cell. Yeah.
So Peter, if you had something like this, how would you, like, how would it be indexed? Like,
so
sorry.
yeah, so something like this would contribute to the left-hand side as so we have two cells, z0, so z0 squared times z1, z negative 1, and if we sort of add up all the possibilities there, we would get so I guess I could work out the product, but it'd be yes, so then we take sort of the exponent being sort of the entry in that cell of each z to the z based on the content. So like instead of just like sort of going by like how many cells we have, we're looking at the how many cells in sort of each diagonal.
Oh, so for example, this power would be the trace of the.
Yes, so like the k, so sort of like the what we called the K trace, so the trace along the kth diagonal, where the K is the content. So it's just the difference of the entries.
So are there other questions to Peter?
There was a question in the chat saying if it was seed 0 to the 2 instead of to the 3. But I think that was Kai.
Oh, was there a
For
mistake
the
somewhere?
example that Alejandro just deleted. But the diagonal has 0.
Yeah, I was wondering if the sigma had to match up to the size of pi.
Sigma had to match up to the size of pi.
We're not as long time for me too, so I probably might be misthinking. But
so were you asking how do we get from the multivariate to the?
No, I think I was just adding on to Sunita's question about the sigmas of the power of z sub the content of the v. So in that example that Alejandro had, the contents were 0, 0, 1, and -1. So I was confused if supposed to be 0 sub z sub 0 to the power of 2 because there are 2 of them, or if I'm misremembering the definition of sigma.
Well, sigma is just a RPP, so I guess in that case, sort of both of those would be taken care of in the product. So there would be 2 factors of that, if I understood the question.
So the power of the variable is the value that is in the box, right?
The value of the variable is the sum of the entries on the diagonal, like a trace.
Right. So then when you multiply them together, it becomes the same.